Hi, I'm Shaun from ClearCloud, and today I'm going to demonstrate how to create a virtual NAS storage device using Amazon EC2 instances. I'm going to take you through a few introductory topics, and then we'll jump into creating the NAS system and hooking up a Windows server using iSCSI. First, we'll cover some of the limitations of Amazon EBS and the general cost structure around storage. Next, I will describe the overall architecture of the NAS system. Then we'll dive into the details of actually creating the NAS and a backup and hooking it up to a Windows server. Last, we'll wrap up with some advanced topics and enhancements that would make the system production grade. Because this is a video about enterprise storage, I want to include a disclaimer. The bottom line is that if you have valuable information, always make sure that you have a backup. Using a virtual NAS can both save money and create more highly available systems. The first issue with EBS is that Amazon charges for storage based on the amount provisioned. So, if I create a 1 terabyte volume, it will cost me around $100 per month, even if I'm only using 5% of the disk space. Most of us tend to over-provision so that we are not endlessly extending volumes as the users consume free space. So the aggregate impact of over-provisioning many servers can really add up. By using a NAS with consolidated storage, we can eliminate some of that over-provisioning by having one central pool of storage that can be shared across lots of servers. Another issue with EBS is that there is no compression, and the snapshots that are taken of EBS volumes are also not compressed, although they are at least incremental. It's also very difficult to automate the management of snapshots, especially when you end up with tens of thousands of them. Because ZFS allows for native compression of volumes and snapshots, you can realize significant cost savings over standard EBS volumes. The last point is that EBS is not durable. The published failure rate is 0.1% to 0.2% per year, which means if you have 100 volumes, you have an up to 20% chance to lose a volume in any given year. Because ZFS natively supports RAID parity striping, you can create durable storage on EBS that is effectively the same as S3, but doesn't have any of its limitations. The architecture of the NAS system is actually quite simple. It's based entirely on free and open source tools and is relatively easy to configure. The heart of the NAS system is a Linux server with the ZFS file system installed. The most useful feature of ZFS is that it's a journaling file system, so it natively supports taking point-in-time snapshots. Many tools have been designed around ZFS, including compression, monitoring, and sending snapshots to remote servers. The connection from ZFS to Windows is accomplished using iSCSI, although you could also create an SMB file share. However, managing permissions gets quite messy, especially in an environment using Active Directory. Now we're going to create our EC2 instance to support the main NAS. First, we'll select Ubuntu 18. I'm going to select a T2 micro for demonstration purposes. I'm going to create the VM in US East 1C. Then I'm going to make the root volume 25 gig, and I'm going to add 6 additional volumes of 8 gigabytes each that will serve as my RAID array. We'll add a name tag to indicate that it's our main NAS. For the security group, we're going to allow port 22 from anywhere for SSH, and we're going to allow port 3260 from our VPC for the iSCSI connection. And we'll go ahead and launch this one, and then we'll launch the backup NAS. For the backup NAS, we'll again select Ubuntu 18. We'll use a T2 micro just for demonstration. And here we'll select a different availability zone so that our backup is in a different location than our main one. We'll again create a 25 gigabyte root volume and add 6 8 gigabyte volumes for our RAID array. We'll add a tag to indicate that it's our backup NAS. And we'll use the same security group, port 22 and port 3260. And then we'll go ahead and launch that. Next, we're going to create the Windows instance that will be used to demonstrate connecting to the NAS. I'm going to select Windows 2019, although you can use pretty much any version of Windows Server or even desktop to connect to this NAS. I'm going to select a T2 medium because of performance issues. We're going to use the same availability zone as our NAS for performance reasons. We'll accept the default storage. We'll add a name tag to indicate that it's our Windows server. For the security group, we'll allow RDP from anywhere. And then we'll go ahead and launch that. Now we are going to configure the ZFS file system and iSCSI target on the main NAS. I'm going to log in to my main NAS using SSH, and then I'm going to switch over to root and do an apt update to make sure all my repositories are current. Next, we'll install the ZFS utilities package. And then I'm going to run an lsblk to look at all my block devices, and we can see that we have xvdb through xvdg. Those are my 6 NAS devices. I'm going to create the RAID pool using those 6 drives, and note the parameter RAID Z2, which means that there are 2 stripes of parity. Creating the pool automatically creates a directory and a mount point, which I've called volume 1. I'm going to set compression on the pool using LZ4, and that compression will be inherited by all file systems underneath that pool. Now we're going to install the TGT package, which provides support for the iSCSI target. And now we're going to create the file system under my pool. I'm going to call it test data. And you can see that it has created a directory representing that file system underneath my pool. That'll also show up in our DF results as a separate mount point. To support the iSCSI target, we're going to create a file in the file system using the dd command. In this case, I'm going to create a file called edrive.dat, and I'm going to assign it a size of 100 gigabytes. Note that the size of the file exceeds the underlying pool size, which is allowed because of the compression. Normally you wouldn't back yourself into a corner like this. I'm just demonstrating that I can do this. Now we'll create an iSCSI target config file, and that will allow us to connect from the Windows server to this file store that we've created in our ZFS file system. Now that we've saved that file, we have to restart the TGT service, and note that restarting the TGT service causes all current iSCSI connections to drop. So if you have any other servers connected, they'll be hard dropped, which could result in data loss. So finally, we can view the status of the iSCSI target and see that everything is connected and running properly. You'll also want to install the sysstat package so that you can monitor IOPS on the instance and in the Z pool. To check our current configuration, you can use ZFS list, which will show all of the current ZFS volumes, and you can use zpool status, which will list out the status of the pools. In this step, we will hook up our Windows server to the iSCSI target. In order to ensure that our iSCSI targets will be reconnected after reboot, we need to set the SAN policy. Open an administrator console window and, using diskpart, set the SAN policy to online all. If you don't take this step, you will lose all your volume mappings after a restart. Now, start the iSCSI initiator and configure your target. You may be prompted to start the iSCSI service if this is the first time that you are using it. In our case, we're going to enter an IP address, although in a production environment, you would probably use a DNS name. After a refresh, you will see the target name that you created. Select it and click Connect. Now, head over to Disk Manager and create your Windows volume, assign a drive letter, and format that volume. Note that you can assign a block size, which is important depending on the workload that you are running. You can also assign block sizes on the NAS in the iSCSI target for further optimization. Once this step is complete, you will have a new 100 gigabyte drive attached in Windows and mapped to a drive letter. Now head back to the iSCSI initiator, select the volume mapping, and pick Auto Configure to make this drive mapping permanent. If you don't take this step, a reboot will clear the drive volume associations. Creating the backup NAS is the same process as creating the main NAS, except we won't install or configure the iSCSI target. I'm going to speed up the video now to avoid the redundant installation. I'm going to create a Z pool called Backup. However, I won't create any file systems under that pool. We'll save that part for when we perform the snapshot replication. In order to enable replication from the main NAS to the backup NAS, we first have to configure the backup NAS to allow the main NAS to log in using SSH. We're going to do this using an SSH key. On the main NAS, generate a key, and then display it, and then copy it to the clipboard. Then, on the backup NAS, you're going to edit the authorized key file and append your newly created key to that file. Make sure that you copy the entire key and that you don't delete or alter the Amazon created key. Once SSH is configured, you are ready to send snapshots from the main NAS to the backup NAS. First, take a snapshot of your file system using the ZFS snapshot command. You can call the snapshot anything you want. For my example, I use the date and time. You can see that the snapshot exists on the main NAS. On the backup NAS, you can see there is the volume, but that there are no snapshots. Now, we will send the snapshot from the main NAS to the backup NAS. Because it's the first snapshot, we're going to use the -F option to force creation of the file system on the target. SSH requires us to acknowledge the very first login. After this, it won't ask us again. Now you can see the file system and the initial snapshot both exist on the remote machine. Now we'll take a second snapshot on our main NAS and pretend that it's a day later. In reality, you would probably want to do this much more frequently, perhaps like every 5 minutes, depending on how quickly your data changes and your tolerance for data loss. You can see that we have 2 snapshots on the main NAS now. We'll send the second snapshot over incrementally. The format of the command is a little different. It includes the -I parameter, and you have to give the old and new snapshot names. Also, the destination just lists the target file system, not the snapshot name. Now you can see that our second snapshot is on the backup server as well. I'd like to leave off with a few ideas about enhancements and some common issues. This kind of system needs active monitoring so that you don't lose data. For example, if an EBS volume goes bad, you will want to know right away. You can check the status of the pool using the zpool status command. This will indicate if there are any failed or degraded devices. You probably want to check this at least once a minute to quickly catch and remediate any issues. You will also want to monitor if the replication fails due to network problems or instance outage. For most systems, you will want to design some way to automatically retry snapshot sends and send alerts after a few failures. You also want to check if you are running out of space on either the main NAS or the backup NAS. This can be done with the ZFS status command or the df command. If you run out of space, the iSCSI target can fail to write or snapshots might not be able to be sent. To fix this, you will want to delete older snapshots to free up space, all of which should probably be automated. You can do most of this with a cron job or by using the AWS CloudWatch agent for monitoring or other automation tools. We developed a REST API server in-house so that all of this could be controlled from pretty much any mechanism like Lambda, Autotask, or a central console on a website. You will want to watch the IOPS on your EBS volumes and the overall instance IOPS limits. These settings need to be carefully considered when designing your NAS so that it is not too expensive and still performs correctly. As I mentioned before, it is possible to do block size matching on the iSCSI driver and the NTFS system. This is most useful when running applications that have specific block size requirements like SQL Server. It's possible to do cross-region replication using the snapshot replication technique. Just set up an IPsec tunnel between the two regions, then configure your snapshot replication job to send to the remote region server. ZFS allows for read and write caching natively. You pretty much want to avoid write caching at all costs unless you don't care about the data, because the loss of the instance will probably result in data corruption. You can safely use read caching in almost any scenario, although you probably won't see much performance gain unless you use a really high provisioned IOPS volume or instance storage. Instance storage is ideal for read caching, and unless you are using it for something else, it should definitely be implemented. Finally, ZFS allows for several types of compression. I demonstrated LZ4, which is really fast and will give you 2-to-1 or 3-to-1 compression in most instances unless the data is really random or already compressed. LZ4 is a good choice because it uses almost no CPU and has no real impact on IOPS or throughput. For less demanding workloads, you can use gzip, which has 9 levels of compression. This is much more CPU intensive, although if you are already using a high IOPS instance like an X or I class, then this is not really an issue. You can experiment with what combinations of instance sizes give you the best performance versus storage compression to come up with the lowest total cost solution. Also note that sending snapshots can be compressed using gzip on the fly to save time and inter-AZ or inter-region bandwidth at the cost of higher CPU. I hope you found this video informative, and please feel free to email with any questions.